How are you? All right. Sort of at the very basic core, magnetic fields are created by moving charges. And when we talk about magnetic fields, we talk about the magnetic domains. Magnetic domains, let's see, we talked about this already? Yeah, a magnetic domain is just a region of uniform magnetization. So if I imagine that I have this electron, an electron is gonna move back and forth, back and forth. That's going to generate a magnetic field. This moving charge causes a magnetic field. I think we'll get into this in one of our later chapters as we sort of explore magnetism more. But this moving electron generates a magnetic field. And when I have a bunch of electrons together, they're all sort of aligned in the same direction, we call that a magnetic domain. So a magnetic domain is when you have this group of electrons that are all oriented so that their magnetic fields are all in the same direction. So within a material, you have this small region of uniform magnetization. Okay? So like within you have these magnetic domains, because we all have electrons, right? Electrons are in everything. So we all have these magnetic domains. And in most materials, the magnetic domains are oriented randomly, like in this one, and that gives us a net magnetic field of 0. So we have these magnetic domains in this material, and they're all, each one represents a group of electrons with all their magnetic fields in the same direction, but these are all added up randomly, so it gives us a magnetic field of 0. My magnetic field here equals 0. But in some materials, like a permanent magnet, the magnetic domains are all lined up, and this gives us a net magnetic field that's, greater than 0. That's in the direction of the, in which they're all aligned. So permanent magnets are created when molten metals cool in the Earth's magnetic field. Or solidify in the Earth's magnetic field. If you can imagine that you have this volcano, I'll draw you a picture of a volcano here. This is a volcano. It has molten lava that's coming out of it, and then this molten lava flows down the side of the mountain. And this is all occurring within the context of the Earth's magnetic field here. And so when that molten lava, when it cools, when this cools, it's going to, the magnetic domains within the lava will be aligned by the Earth's magnetic field so that you'll get a magnetic field within that lava that's all aligned. And so that's how they generate magnets in nature. That's how we get magnets in nature. And then that's also how you create magnets in the lab as well. You can also generate electromagnets. And electromagnets use a moving charges in a wire. Okay. Right. That's just a fancy way to say a current. To create a magnetic field, and that aligns the magnetic domains in the material. So if I imagine that I have a coil of wire, and I have it around, say, a piece of iron, a nail, or whatever, the magnetic domains are all just sort of randomly oriented. But when I run a current through this wire, that causes a magnetic field due to the current in the wire. This is called a solenoid, which we'll talk about later in this chapter. And then that orients the magnetic domains in that wire. Right. You've done this before, right? Where you wrap a nail with a wire, that causes an electromagnet. We're not going to watch this video, it's just some kids who make these. All right, let's try these. Look for questions. you'll see some basic multiple choice questions just about magnets and how they function. Sorry, I'm in my 7:30 class here. Right? Counting, we don't have much longer, just Alright, just a few more seconds. Stop at 103. Alright, very good. Alright, they're magnets because their magnetic domains are all aligned. Not because they contain charges. I mean, you contain charges, right? But you're not magnetic. And not because they're metal. Not all metals are magnetic, like aluminum, for example. Not only is it not a permanent magnet, but its magnetic domains can't be aligned. That's why magnets aren't attracted to it, and not because they're found in the center of the Earth. Let's see, one of y'all told me this. I'm not going to tell you who. If you don't like it, then you won't be upset. But let's see. Do you know how you can make any salad a Caesar salad? No, by stabbing it a bunch of times. That's pretty good. I wasn't sure how I was going to go over. That's pretty good. Right? Pretty good joke? Yeah. Alright. Which of these best explains why a permanent magnet is magnetized? About 10 more seconds. Stop at 52 or 50. Miss everybody. Yeah. Okay, good. Still, because of these magnetic domains, a permanent magnet, in fact, does not have a current through it. You can create an electromagnet by putting a current through a wire. We'll see that later, that anytime we have a current through a wire, it generates a magnetic field. That was one of the discoveries sort of late 19th century that allowed for the production of electric motors and electric generators. But a permanent magnet's because the magnetic domains are aligned. Okay, just a few more simple things on this, and then we're going to get into cross products and what have you. We use magnetic field lines to represent the magnitude and direction of B fields. And we have a couple of rules that are similar to those that we had for electric field lines. Remember electric field lines, we had those, the density of the lines represents the magnitude of the electric fields. They start at positive, end at negative charges, those sort of business. We're going to have similar rules. The first rule is that the magnetic field lines begin at the North Pole and end at the South Pole. Alright, and then the other one is that the density of the lines is proportional to the magnitude. It's proportional to the magnitude of the B field. Alright, so here for example, notice I have magnetic field lines, they run from here down to here, from north to south. Here it's drawn this way, but really it's implied that these lines come around and wrap back around. You can't, like when we had electric fields, remember if we had one charge that was bigger than the other, you had field lines that would sort of go off into infinity. That's not going to happen here, because you can't have one side that's more north than the other side is south, right? Because you can't have a monopole. You can't have just the north or just the south pole. So all these lines actually connect because of that idea that you can't have a monopole. All right, also Earth's magnetic field. Compass needle is a magnet with a north and a south pole. In fact, Dr. Baker, you remember Dr. Baker? Yeah, he used to always, we would go out and like do stargazing and stuff at night, because he was a really pretty good amateur astronomer. I don't know if I knew this about him. He's certainly much better than I or my wife are. We're professional astronomers. But he was a really good amateur astronomer. And when you're setting up a telescope, you have to align it with the North Star. When you put the telescope down, you just want the telescope to be aligned with the north-south direction too. So you need to know what north and south is. And of course, we bring out our compass, right? Because that's what you do if you want to know what is actual north. But he would bring out a bucket of water and a magnet, and the magnet was like on a little piece of wood, so it could float. And you put the magnet in the water and use that to find north and south. That's just sort of the way that he was, right? Did y'all know him well? He's been gone for a while, but he's just kind of a quirky guy like that.
Like, don't worry, I've got my compass with me.
Right, I got my bucket of water, my wood, my magnet. I liked him. I understand that some students didn't like him very much, but he was a good guy. I liked him a lot. Did y'all like him? You never had him for a class. Yeah, I understand he was pretty tough. All right, so Earth's magnetic field, a compass is just a magnet, has a north and a south pole. And the north pole of the needle, the north pole of that magnet points north, as you might expect, and the south pole of the needle points south. Those are our geographic north and south, and that's how we define them. But if we imagine that, the planet is a big bar magnet, so for example, here's North America, there's Florida, there's South America, there's Europe, there's Africa, sort of. Where we have our northern geographic pole is actually where we have our southern magnetic pole, and vice versa. Where we have our southern geographic pole is where we have the northern magnetic pole. You'll follow what I mean? Because if I have a compass, right, and the compass is just a magnet, the north pole of the compass points to the north pole, like where the polar bears are, and the south pole of the compass points to the south pole, where the penguins live. And that means that the south pole is actually pointing to the northern magnetic pole. The magnetic pole and the geographic pole are opposite. And actually, they're not perfectly aligned either. The northern magnetic pole is off shift from the southern geographic pole and vice versa. But that's not really helpful. But just the point is that they're different. They're reversed from what they are. Let's see, have y'all seen this movie Without a Paddle? I understand it's a good movie is what they say. Is it good?
You can't do anything else with it.
Oh, well, you can't have local fluctuations in the Earth's magnetic field. I guess you'll talk about this, geomatic folks? The Earth's magnetic field very much.
They kind of say like when you use certain issues you might have certain things on them.
Okay, because it can affect the Earth's. Well, you can have local fluctuations in the Earth's magnetic field. In fact, you can go online. If you just Google sort of Earth's magnetic field, you can find a website where you can find actually the Earth's magnetic field for a particular location. So it's something like 20 or 25 microtesla per year. But those fluctuations can be due to geological features like big iron deposits. Iron is a ferromagnetic material. In fact, iron is, what's another word for iron? Something's made of iron is what? Huh? Okay, metal, but ferrous means iron, right? So that's where the word comes from, ferromagnetic. A material that can become a permanent magnet is ferromagnetic, that its magnetic domains are able to be aligned to
that means.
So you can have local fluctuations in the Earth's magnetic field. All right, let's try this little quick test. Which pole of the magnet points towards the magnetic north pole?
Another thing about the whole equipment stuff, when me and Dan, like we did land nav in the military,
Mhm.
and you give them this compass, and you actually have to take your rifle and strap it to your back, or give it off to somebody so it doesn't affect the, it doesn't miss the magnet.
Oh, cool. That is cool. Yeah, yeah, the magnet's attracted, I guess, to it. All right, let's see, just a few more seconds. All right, let's see. The magnetic north pole is attracted to the south pole. All right, remember to go back to that figure that we had before. The picture of the Earth, I'll just redraw it here. So if I have my Earth, North America, South America, Europe, Africa, this is the geographic North Pole, but it is the, if I draw a bar magnet, it is the magnetic South Pole, and this is the magnetic North Pole, and this is the geographic South Pole, right? Because of how we define those poles based on the magnet on our compass. All right. Also, the magnetosphere, because the Earth has a magnetic field, I can imagine it as being a bar magnet. And remember, if we draw the field lines of a bar magnet, they sort of look like this, running from the north to the south pole. And in a similar way, there's a lot of cool stuff that goes on with the Earth's magnetic field. So this is just an artist's depiction of the Earth, the sun, not the scale, obviously, but the Earth has this magnetic field. And it's a good thing too, because the sun is constantly putting out this barrage of high energy particles. The sun is primarily a plasma, which is an ionized gas, right? And it's constantly shooting out these ionized particles towards the Earth. They're very high energy particles, so if we didn't have a magnetic field, it would strip the atmosphere off of the Earth first, and then it would kill everything on it. That could be very bad, obviously. But the Earth's magnetic field helps protect us from this barrage of particles from the sun. I have a little simulation and a video about it. All right. All right, let's look at the cross product. We did this last semester when we were doing angular momentum. We're going to see it again here. So just a quick review on what is a cross product. The cross product is also called the vector product. We use this anytime we want to multiply two vectors that are perpendicular to one another, two orthogonal vectors. So the cross product is simply a way to multiply the magnitude of one vector that is orthogonal to the magnitude of another vector. And then we'll get a third vector, which is the product of these two, that'll be orthogonal to those two vectors. Y'all know what orthogonal means? It means at 90 degrees to, perpendicular to. I don't know why they use...
Another word for perpendicular then?
Yeah. I think it's actually more complicated because usually we talk about orthogonal coordinate systems, and that means like if this is our x, y, and z axes, the x, y, and z axes are orthogonal to one another. So if this is 90 degrees to this is 90 degrees to this, and they're all 90 degrees to one another. All right. So the vector product, or the cross product, is the product of two vectors. And the result of the cross product is orthogonal to both of the two vectors. Alright, so if I have one vector in this direction, one vector in this direction, then the product of those two is going to be in a direction that's orthogonal to both, like in that direction. Alright, the magnitude of the cross product is equal to the area of the parallelogram that's bordered by the two vectors. So if I had two vectors A and B, A is the blue, B is the red. If I want to know if I take the cross product, A cross B, the magnitude is going to be equal to this area of this parallelogram. And so the area of the parallelogram is like this. I have a picture on the next page. The area is equal to the base times the height, and that's equal to the size of one vector times the size of the other vector times the sine of the angle between them. And that's just sort of mathematically how we find that area. So the magnitude of this cross product then is equal to A times B. That's the magnitude of A times the magnitude of B times the sine of the angle between them. If you also want to think about this in this way, let's say that I have a vector A here, and I have a vector B here, and I want to find the angle and the angle between them is theta. If I want to take the vector product or the cross product, remember the cross product is the product of two vectors that are perpendicular to one another. So B is not perpendicular to A, but B is perpendicular to a component of A, right here. And this is equal to A sine theta. So it's like taking the product of B, the magnitude of B, and the magnitude of that A sine theta. And so that's where this sine theta term comes about when we're doing the cross product. Has lots of applications. In particular, we're going to use it for the force on a particle that's moving in a magnetic field. Let's just do an example. Let's say that I have two vectors, A. We'll say that A is AXI plus AYJ. B is BXI plus BYJ. Remember how to do the cross product, sort of, from last semester? Sort of, kind of? Alright, so the cross product, if I just do FOIL for these two, remember FOIL first, outer, inner, last. If I do first, that's going to be AX, BX, I cross I, plus the outer is AX, BY, I cross J. Inner, what's inner?
AYBX.
Right, AYBX. Just multiplying out these two functions, A times B. AYBX, that's J cross I. It's very important that you get the order of the vectors correct, otherwise the answer won't come out right. Plus, last is AYBY, J cross J. Alright, I can get rid of some of these terms because I know that A cross B is equal to AB sine theta. Some of these terms will go away. They'll go to 0. Which of them will go to 0? For which of these is sine theta equal to 0? Sine of theta is equal to 0 when theta is equal to 0, right? So which of these, I cross J, J cross I, or J cross J, which of those pairs of vectors have an angle between them that's equal to 0 degrees? Right, the ones that are in the same direction. So I cross I is equal to 0, and then also what? J cross J is equal to 0. So my product then is going to be AXBY, I cross J, plus AYBX, J cross I, when I get rid of those. Alright, then we're going to use our right-hand rule. We did this last semester. You remember the right-hand rule? We're going to do it quite a bit, actually, in this chapter, because the right-hand rule describes the directions of things, magnetic forces, and magnetic fields that we'll use a lot in this chapter. So with our magnetic field, we can hold it, if we hold our right hand like this, the index finger is our first vector, our middle finger is our second vector, and then our thumb gives gives the direction of the cross product. So you're going to let the index finger of your right hand go in the direction of the first vector, and the ring finger, or that's not your ring finger, your middle finger, excuse me, go in the direction of the second vector, and then the thumb of your right hand gives the direction of the cross product. Alright, so if we go back to what we were doing, we had I cross I. Now you already told me that this and this are both equal to 0. But if I'm looking at I cross J, what is the direction of that cross product? I cross J. Remember, index finger in the direction of I, ring finger or middle finger in the direction of J. And so what's the direction of, is the plus K direction out of the board, right? So I cross J is plus K. What is J cross I? It's just the opposite. It's going to be negative K. That's one property of cross products. I'll get into this in Calc 3 if you take Calc 3. But A cross B is equal to the negative of B cross A. So if you ever do two vectors, the cross product of two vectors, and then you just switch them, it's just going to be the negative of that. So while I cross J is plus K, J cross I is minus K. Alright, so then our cross product from that original one that we did is going to be AXBY minus AYBX K. Because our I cross J is plus K, our J cross I is minus K. Alright, we can have cross products, and we'll see them where we have the cross product is in all three dimensions, and we'll see some of those later. But in this case, we just have one dimension. Alright, we are gonna use these symbols too. We've seen these before, but just to remind you, if we're going in the negative Z direction, that's like an arrow going away from you, we'll use a circle with an X, or maybe just an X. It's supposed to look like the fletching of an arrow as it goes away from you, the feathers on an arrow. And the plus Z direction is supposed to look like an arrow coming towards you, like that. Right? Or like a circle with a dot on it. So if you have an arrow coming towards your face, that's what it would look like. Alrighty? Cross products? Remember? You'll see a cross product on your test. So for magnetic forces, our cross product, our force of a charge moving through a magnetic field feels a force that's equal to QV cross B. Because of the definition of cross products, this has a magnitude that's equal to QVB sine of theta, where these are the magnitudes of those vectors. The SI for the unit for the magnetic field is the Tesla. After the famous scientist, Nikola Tesla, there have been several movies about him. He was kind of a quirky guy. We'll listen to a clip later when we get into sort of electricity and how it works. And sometimes, we won't use this here, but sometimes you'll see magnetic fields expressed in Gauss. Often the Earth's magnetic field is expressed in Gauss, but we won't use it here. We'll use Tesla instead. Alright, we're going to do some right-hand rule stuff, so just finding the direction of the force or the magnetic field. This will get a little tedious at times, and we'll do it quite a bit, but it's useful just to help you think in three dimensions. That's really the primary thing. And then also, we'll apply it when we're doing cross products as well. So here I have some different configurations. I have charges moving in a magnetic field. These are all positive charges, and I want to know what is the direction of the force. Now remember, our force is equal to QV cross B. So we can use our right-hand rule, let our index finger go in this direction, let our middle finger go in this direction, and then our force is given by our thumb. All right, so what is the direction of the magnetic field for this first, or for the force on this positively charged particle for this first one? Let's see, so we're going to have, no, it's like this. Right? No, that's not right. Which is it?
You said your D is
Out of it.
so it would be
Yeah.
like that.
It's going to be out of the
middle.
Right. How many voids? One key thing is that, you know, these are all orthogonal. So if V is on the x-axis as it is here, and V is on the y-axis as it is here, then the answer has to be along the z-axis, either along the plus or minus z-axis. So here, this one is coming out of the page. The force on this particle is out of the page. How about this next one? Here my magnetic field is going into the page. Index finger is going to go in the direction of V. Our middle finger will point in the direction of V. So what's the direction of the magnetic field? It's to the right. In the, yeah, so it's going to be in this direction. All right. How about this one? V is out of the page. V is down. To the right, yeah. Listen, another way that people do this is to let all the fingers go in the direction of V, and then you imagine the magnetic field coming out of your palm. And so you let your fingers go in the direction of V, and then they will fold towards the magnetic field, and then your thumb will point in the direction of the force. So here, it's, what was it, to the right? So that's our force. You can work backwards as well. So like, say you know your force and your velocity, you can determine your magnetic field. And we'll see this also with the mass spectrometer. This is the principle behind the mass spectrometer, how it works. You have a mass spectrometer in the department? I don't think you do. Do you? I don't think you do. Alright, but you might use one in the future as you go into, you know, whatever it is that you do. Alright, so what is the direction of the magnetic field that causes this force? Here I have a positively charged particle that moves upward, and it feels a force that's out of the page. What is the direction of the magnetic field that has caused this? Let's see, yeah, so Z is in this direction, F is out of the page, yeah, so it's going to be to the left, the magnetic field. If you're not getting this yet, don't sweat it. We'll do this on the concept test to give you a little more practice. But you will see some multiple choice questions, maybe even a 3-response question that has to do with this. All right. What about the magnetic field that creates a force here? I have a velocity that's into the page, and my force is to the left. What magnetic field has caused this force to act on this positively charged particle? Down. What is that? Let's see, V is into the page. Yeah, down is right. So if our magnetic field here is down. Again, noting that these are orthogonal, so the magnetic field has to be on a completely different axis from the velocity and the force vectors. And then let's do this last one. To the right. Let's see, our force is down. I know my thumb has to be down. My magnetic field is into the page. Yeah, so it has to be... Oh, it's out of the page, isn't it? right? Yeah, to the right. Let's try this quick test question. Here, so if I have a negative charge, the force is opposite the direction of what you would find for a positive charge. So here I have a negative charge. I want to know what direction will it feel a force. In this case, you would just do it as you would normally would with your right hand, and then you would just take the opposite answer because it's a negative charge. Negative charges feel a force that's opposite that of a positive charge. So if it's up for a positive charge, it's down for a negative charge. All right, just a few more seconds. I'll stop at 125, 125. Let's see, we're sort of all over the board here. So my velocity is up. So I'm going to have my fingers going in the direction of V, or you can think of your index finger going in the direction of V. My magnetic field, however, is out of the page. So I have to rotate my hand like this for my magnetic field. That means that this force would be to the right if it were a positive particle, but it's a negative particle. So the force is to the left. All right. Don't sweat it if you haven't gotten this yet. We're going to do it a lot more. Josh?
I think you were told from that picture that B was going out of the page. That's what I was having trouble with.
Oh, okay. Well, remember we use this symbol, just a dot is out of the page.
Okay.
All right, yeah, so, but here I showed a region that has a
So
magnetic
it
field.
would have been like B with a bunch of X's.
Right.
And then it would go into the page.
Right, this would have been into the page.
Okay.
I'm sorry, that was confusing. We'll see some more questions like this as we go along. So if you haven't gotten it yet, don't sweat it. We'll see it again. All right, let's look at this example. I have a proton that's moving at this speed, 2I plus 1J, in a magnetic field, 1I minus 3J. I just want to know what is the force in vector notation and what is the magnitude of the force. Let's just do a cross product. So let's just do this cross product. Remember, our cross product is QV cross V. If you want to express it in terms of E, the fundamental unit of charge, that's fine. So we don't have that 1.6 times 10 to the minus 19. First, just want to write this out. So I'm going to write this in terms of E, which is a proton. 2I plus 1J crossed with 1I minus 3J. Do that cross product, remembering that I cross I and J cross J are equal to 0. If you've had Calc 3, well, none of you have, but if you take it, they teach you a slightly different way to do cross products using a matrix. If you know that way, you can do your cross products in that way if you like. Let me know when you get your cross product, and we'll go to the next step. what's my first term in my cross product? Okay, yeah, so outer negative 6 I cross j, which is going to be positive k, right? And then what's my next term? First, outer, inner. I have inner, right? Right, so that's plus 1 j cross I. What is j cross I? Negative k, right. So I have negative 6k minus k, so it's going to be 1e times negative 7k. Put something over here. All right, so that is so anyway, that's our force. Our force is negative 7 times 1.6 times 10 to the minus 19 in the k direction. That's in newtons. We'll come back and finish the rest of this. I have a problem with my notes anyway. We'll come back and finish the rest of this on Monday. All right? Y'all good on this? Cross products? Josh, you have a question?
No,
Okay. Don't worry, we'll do it some more. So if you haven't gotten it yet, we'll see it again. What is it? Everything okay? Yeah. Okay. All right, y'all. I'll see you later, okay? Have a good weekend.